All right, section 115. We're looking at horizontal asymptotes, and we're concerned about the end behavior, what we used to call LEBs and REBs, right end behavior, left end behavior, and what's it doing when you go far to the left, like negative infinity, and what are you doing when you go far to the right, like positive infinity? So it's like taking the limits. So the limit as x approaches negative infinity for your function, and the limit as x approaches positive infinity for your function is going to help you determine what the horizontal asymptotes are. And so he went into this big explanation about, well, the denominator grows faster than at 0, which is true. And if the numerator and denominator grow equally fast, then it's 1, but that's not necessary. Well, yeah, I guess that's true. If the numerator grows faster than the denominator, then you have infinity. Now here's how we used to talk about it back in the day. We said, if you have a bigger power on top and a littler power on the bottom, big over little, there's none. If you had little over big, it's y equals 0, which is the x-axis. That's what he's saying up here in this first bullet point he's got. And then we said if it's the same, if they're the same powers, top and bottom, then you take the coefficients and that creates your horizontal asymptote. So that was in our language how we've always done it. Same thing applies here. Then he went into this big explanation about which function grows the fastest, and that's kind of important to us a little bit. But really the one that you want to pay attention to is this guy that's 4 to the x, the exponential function. That grows really, really fast. Faster than anybody else. The rest of these graphs, if you were to graph them, they grow, but they don't grow really half as fast as this 4 to the x. So out of all of this stuff that he put here, the piece that you want to remember is that this exponential guy is the guy that grows fastest. These logarithm guys don't grow very fast at all. They're the ones that kind of like, they just kind of go like this. The logarithm graphs, they just kind of come up the y-axis and then go off to the right. They grow. Inverted. What's that?
They're like inverted exponential.
Yeah, exactly. So it's an inverted exponential graph. So what you end up with is something that grows, but it just doesn't grow as fast. All right. So let's go in and then let's think about this as we would think about this, because I know he went into all sorts of explanations and things. But where's the bigger power? Number 4, bigger power is on top. Big over little, there's none. Number 5, they're the same powers. Take their coefficients, 1/3. Number 6, little over big, y equals 0. Number 7, you have to do some foiling to figure out what the highest power is. So I have an x times an x up top, I'll have an x squared. I have a 4x that's being squared, that's a 16x squared. And so when I do that math, I end up with 1/16 because they're the same powers. The ones with the roots can be a little bit more tricky because sometimes it's plus and minus, and sometimes it's not. So for this one, if I take 4x squared and I square root that, I get a 2x, and on the bottom I have a 3x. And because it's being squared, it's going to be positive or negative. So you've got horizontal asymptotes that are at plus or minus 2/3. And then he used the example over here to show you the difference of why when it's not plus or minus. And it's not plus or minus for this guy because if I take the square root of 4x to the 4th, I get 2x squared. And anything I would put in there for x is always going to be positive because I'm squaring the value. So it's only the positive 2/3 for this guy. So there's a difference between these two. This one, because when you take that square root, you get a squared value, it's always going to be positive. Where in the other one, it could be positive or negative. All right, number 10. If I have 1 over infinity, that's like 0, and e to the 0 power is 1. So negative 4 times 1 is negative 4. E to negative infinity, same idea. E to infinity is going to be like 0. So you've got 5 times 0, and that's 0. I think, did you have any more? A couple more, yeah, a couple more on the back here. Number 12. You needed to remember, and I put it in my margin, these two fact things that we talked about a while ago. So if you take the limit as x approaches 0 for the sine of x over x, it equals 1. But the limit as you approach positive or negative infinity for the sine of x over x, it's 0. I gave you a quick little picture to remind you of what that graph looks like. it kind of bubbles up at the y-axis, gives you a little hill there, but then it goes oscillating as you go out, and it gets closer to 0 on either end. All right, so those two are fact things that are going to come up into play to do these problems. So first one is just this directly at 0. The next one is if I plug an infinity in, 1 over infinity is 0, the cosine of 0 is 1, negative 3 times 1 is negative 3. And the last two don't exist because think about the sine graph or the cosine graph. They keep bobbing and weaving between 1 and negative 1. They're waving back and forth, right? They don't ever merge towards one particular y value. And so both of those are oscillating and don't exist. Which, by the way, how do you spell oscillating? He spelled it with one.
I was very confused.
Oh, I was too. How, where's Siri? How do you spell oscillating? It has two L's. Thank you very much.
I-L-L-A-T-I-N-G.
I actually didn't butcher that word. I just missed an L.
When I was looking at his notes, I'm like, dude, I think there's two L's in that. And I never got a chance to check it. So there you go. Now I checked it. Now we're good. Man, we're overruling him on all sorts of things in this section, aren't we? Okay, poor guy. So let's try some practice problems. I'm going to take requests from you. I did not mark up ones that I wanted to pick.
Yeah, 5.
Number 5, you got it. Shoo, look at number 5, right? All right, you're all about trying to compare the powers. So if you're looking at number 5, I have to take the square root of that thing. Well, 7 ain't no pretty square root, right? So if I take the square root of that, it's just going to stay the square root of 7. But I can make this outside of the root an x cubed. Right? That's my top. My bottom, the highest power down there is an x cubed. Oh, wow, they're the same. If they're the same power, then it's just whatever the coefficients are. So it's going to be y equals the square root of 7. Right, right. That was the next thing that's going to come up. So is it positive? Is this one of those that's a positive or negative, or is this just a positive? Right, and this guy is going to be one of those plus or minuses for this one because you can have either a value that comes out that's positive or negative from a cube. I think number 6 is one that stumped me a little bit, made me think a little.
Yeah.
Yeah?
I was in between two answers.
Okay, yeah, because this one, number 6 is one that when I looked at it, I was like, oh my goodness. All right, so if I square root my 9x to the 8, that's going to be a 3x to the 4th. I have a 2x to the 4th on the bottom. Now, this is one that's always going to be positive because if I fourth a number, it's always going to turn out to be a positive answer regardless of if it started out negative, right? Even root. All right, so it's going to be y equals 3/2. Now, however, you're not done. Can you think about why you're not done? Yeah, see this guy at the end? He messes it all up. Think about how we shift graphs, right? Mm-hmm. This now takes that thing and moves it up 3.
Okay, that's nice.
Yeah, so it really is plus 3. Now, if I'm in half language and I want to be talking 3, I'm really 6 over 2. Do you know what I mean? Mm-hmm. Yeah. And so that makes it 9/2. And that's really where it's at. That one was tricky. I think I would have lost. I don't think I would have caught that plus 3, like thinking that way so much.
Do you care?
9 or 10.
9 or 10.
Do we care if we write it like 4.5?
Nope. You can write it as 4.5. That works too. 9 and 10 are the next ones that are being requested here. Let's take a look. If I look at, I have to do these kind of separately because one's talking sign language and one's talking polynomial language, right? If I put an infinity into this, so this first one is going to be what's the sine of 1 over infinity?
0.
Yeah, it is like 0. Let me keep going with that. The sign of 0, so you go to your unit circle, what's the y value at 0? All right, 0 minus, right? We've got this subtraction thing going on. And then I'm looking at, what's my horizontal asymptote here?
2.
2. Right, so toss that 2 in there and you end up with an answer that's negative 2. And number 10 that you were talking about, if I put an infinity in, now I'm 5 times the cosine of 1 over infinity. Well, 1 over infinity is 0. So it's really 5 times the cosine of 0. Cosine of 0, go to 0 in your unit circle. What's the x? It's 1. 5 times 1. And there's your answer for that guy.
Can you do 11 too?
Yeah, no, that's why I'm glad you're here taking requests. 11's kind of goofy because you can't make a comparison off those powers, can you?
Yeah.
Which makes this a little bit different than others that we've done. So then you got to think about, this is where his chart comes in, how these things grow. Who's growing faster?
Exponential.
The exponential guy on the bottom. So that's getting bigger faster. So what's happening to that fraction?
Smaller base 0.
It's getting closer to 0. Right. So you see all the thinking that went into that? That one you didn't have the rules we could do little over big or whatever it was. You just kind of have to think about how those functions are growing. Is the numerator growing faster or is the denominator growing faster? And in this case it's the denominator, which makes that really equal 0. So this guy's is really just a 0 minus 5. Looking to see if there's any others I would recommend. Maybe number 20. What are your thoughts on 20? I go comparison shopping here with my exponents. Bigger guys on top. What am I plugging in there though? Infinity, right. So if I have infinity cubed over infinity squared, who wins? Infinity wins. Yeah. Yep.
So there would just be no asymptote.
Yeah.
So concept does not exist.
So technically, well, here's the difference though. Watch your directions, right? If they were asking you where the horizontal asymptote is, you would say, ain't got none, right? Because it's going to infinity. But because the directions are saying evaluate the limit, it actually has an answer of infinity for this guy. So, yeah, watch your directions. Directions changed as of number 8.
Wait, why is the limit infinity? Sorry.
That's okay. If you have it, no, just think, if you have infinity cubed over infinity squared, what are you left with?
Infinity.
There you go.
I just want to
Providing limits and not asymptotes.
It is because it's,
to like realize we were not doing
yeah, again, the directions changed on that as of number 8. So what they're asking you for is a little different.
But in the practice problems, there would not exist, right? Or oscillating.
There are a couple in here, yeah, like let's go back to 13, right? 13 is negative 3x times the cosine of x. If I'm going to infinity, I am waving, cosine graph, waving until I get to infinity, and I'm never converging on a particular y value. This is one of those that doesn't exist. He's one of those that won't exist. We ready to flip?
Why isn't that one negative infinity though?
Which one?
13.
Because it doesn't exist.
Would it be the same for 14?
Yeah, same for 14. All right, good call. Sine graph does the same thing. It's bobbing and weaving, not converging. All right, let's try flipping. See if anything comes up on the next part. I'm thinking maybe 29. I'm looking at my answer key and seeing which ones
Yeah.
might look.
Yeah, we should do 29 and 30.
Okay. See, I'm glad you're here. You're helping me out here. All right, so I'm looking at number 29, and I'm thinking, like, what the heck was this whole hot mess? So I've got the cosine. I want to evaluate this. And I'm going to use my thoughts about horizontal asymptotes and see if I can narrow this down a little bit. if I look at these two, see how they're both squares? You got your x
Really
squared
helpful.
going on? What's that?
I said that's really helpful. 'cause
It
you
is.
have to, like,
It is helpful because that's really what you're going to figure out what the cosine's doing. Joey is looking. Oh, you want thinking of the unit circle? Are you? You can cheat. It's okay. It's all right. We're looking at the unit circle in the back of the room. Were you missing that? When you were home, you didn't have that. I don't think you do. None of you have unit circles in your room, right? Painted on the walls. Oh, on your little sheets. The sheet. Okay. So think of my horizontal asymptote for this thing, right? This would be, now be careful, there's a negative sign with this. If I take the coefficients because the powers are the same, this is really negative pi over 2. Now negative comes from this subtraction sign that's down the bottom. So what you're doing is you are evaluating what the cosine of negative pi over 2 is. Negative pi over 2 means you're going down to get that angle. So that means that you're landing really at 3 pi over 2. Positive 3 pi over 2 is the same as negative pi over 2. And so what's the x value there? 0. Good. That's your answer.
I'm really confused.
Okay, so we're ignoring the fluff.
Okay.
Okay, so the fluff is the stuff that's not with the x squared pieces.
Yeah.
So if I take and think horizontal asymptote, forget about the cosine, just say I wanted you to find the horizontal asymptote for that. You would take the coefficient of pi
okay.
and the
Alright.
coefficient on the bottom of negative 2. So it's a negative pi over 2, and then that's what the cosine is that you're evaluating.
Alright. That makes more sense.
Yeah, and the same thing goes over here in number 30. And it's kind of confusing because you're ignoring the fluff again, right? You got just take the pieces with the x going on. Now this one's a little tricky. They tried to trick you. Did they catch you? Because really the one that you're comparing it to on the bottom is the cubey, not the squarey. They put them out of order to see if you were paying attention. And so this one's going to now be, you're looking at the cosine of, now think about this, if I have little over big, it's 0. Right, little, this guy, just to make note, you're looking at the littler power on top and the bigger power on the bottom. That's going to be a 0. So what's the cosine of 0? You go to 0, you take the x value, you get an answer of 1.
27.
27. This guy, I've got to find the biggest power on top, that's your 3x to the 6th. And your biggest power on the bottom is an x to the 8th. That means you're doing a little over a big, which means that you have an answer of 0.
Okay. I don't know that.
Okay? All right, anything else from 115? Were there tests? You said the test preps were awful.
Yeah.
Were there any that were particularly bad? I'll do 1 or 2 of those, but
Looking at the back, I guess 36.
36?
Yeah.
Okay.
I'm gonna be honest.
Anybody at home have a request from the test preps on this guy? Look at that with all those letters.
31.
All right, so 31 and 36 will be our 2. All right, 36. 36. There's a whole bunch of letter things going on in here. What the heck?
I don't know what's
You almost look at that and you're like, yeah, right?
and I can't like pronounce it either.
Answer C. The answer's always C. Actually, the answer really is C. All right, well, let's see how that happened. All right, horizontal asymptote first. Well, horizontal asymptotes come from the highest powers, right? So forget all the rest of the gobbledygook in this whole thing, and let's look at who's got the highest power. Well, that would be negative a cubed, negative ax cubed, and negative wx cubed, right? So they create your horizontal asymptote, my ha. I'd have a negative ax cubed over a negative wx cubed, and they're the same powers, so I know I have an asymptote at at positive A over W, right? But they told you what it was. They told you that it equaled 2. All right, so what else did I want to say here?
Because it would be 2 over 1, so that would be 2 minus 1 would be 1. Wait,
Yeah, I guess you could say that, right?
yeah, but that's not.
I'm confused.
All right, let's hold on to that for a minute. Let's go on to the next. What? Did you get? Are you with me that A over W has to equal 2?
Yeah,
I just don't have
but
to do
my
that.
thing is with the vertical asymptote is x equals 0. If you plug that into the original equation and try to get where vertical asymptote is x equals 0, then w has to equal 0.
Wait,
No, W is actually. Before I talk about the next part of this with the vertical asymptote, are we cool with this?
Yeah.
Okay, because we're going to come back and use that in a minute. Let's go vertical asymptoting. Vertical asymptotes come from the denominator, and when the denominator equals 0, correct?
Yeah.
All right, so let's check that out. So that means that E, and I'm working on the VA, it means E to the negative x minus W x cubed plus W has to equal 0. Vertical asymptotes come when the denominator equals 0. Well, they tell you that x is 0. All right, so if x is 0, that means that this is E to the 0 minus W times 0 cubed plus W. Well, what's E to the 0?
1.
Yes, right? Good. Anything to the 0 power is 1. This middle term gets knocked out, it's zeroed. Plus W equals 0, which means that your W actually equals a negative 1. All right, so let's go back to our question here. W minus A. Well, you know W is negative 1, right? And if W is negative 1, then I know what A is, don't I? A has to be a negative 2. And so W minus an A of negative 2 gives you negative 1 plus 2, and that gives you 1. How about that? That was some math.
Oh, okay.
Do you not feel brilliant now that you figured that out? You should be good, like, yeah, happy dance.
That was really. I would get that wrong for the name test.
Yeah, well, you guessed C, so you'd be all right.
I would guess C, too. Yeah, that's
What is e to the power of 1?
E to the power of 1 is E.
Oh.
And E is equivalent to 2.718, yada yada. Kind of like pi is 3.14. E is 2.718.
I am not good at using those. I just forget.
Yeah, logarithms and E's and all that stuff, they tend to
Like, it's not hard. Like, it just never stuck. And then I ended up, like, always remembering it.
you are not alone if you struggle with that.
The swirly dude, I can remember it one way, but not the other.
Oh yeah, that swirls, all the tricks that I tried to teach you along the way. I was just sharing the martini glass slope thing with some of my classes the other day. They're like, oh, I shared Slope Dude with them too. How about that? Slope Dude, remember Slope Dude? All right, 31 was the other one that came up. Let's look at 31, and then we're going to move on to 16. Let's see, 31. So the question is, which of the following grows the fastest in number 31? Remember the chart. Which one grew the fastest on the chart?
The exponential.
And that exponential guy. All right, do we have any of them?
The all.
C.
Well, think about it, is 1/2 to the exponent. Which one of those looks like?
I put C. I think C is, when in doubt, pick C.
It actually, the answer is C.
Yeah.
It is C again, but it's an exponential function. Any exponential function is the one that's going to grow the fastest.
I just assumed because on the front they had more than an X power, so that's quarter to U.
Yeah, yeah.
But
So-
why isn't it like
I
B?
just don't understand.
Why isn't it B?
Common answer would be
Because
C.
if you have an exponent that stops. See how the exponent is 100 or 99? It stops. That's not going to continue to grow. It's going to stop at some place. I mean, it's still going to grow a lot, but not as fast as this guy, because this guy over here, it's going to keep growing and it's never going to stop. It's never stopping. He just grows and grows.
So why isn't it
Why isn't it D?
Would be like 400.
Because E is equivalent to 2.718.
Like 2.
So, like, this would not grow as fast as a 4 would grow.
Yeah, because I just, I did 200
I'm gonna
times the 2.
Yeah, exponent. Yeah, please excuse my dear Aunt Sally. Good thought. Good thought on that though too. Some of the kids here in the classroom are saying they just took the 200 and multiplied it by the 2. Then that would be bigger than the 4. But you have to do the exponent before you multiply by the 200. So good call on that. Good thing to remember. All right, we ready for 16? 16 is a big deal with the intermediate value theorem. And again, his explanation was perfectly wonderful, except I think it kind of got confusing at times. Again, these two sections, they're really pretty simple. Oh, here. I should be wearing a ribbon saying stay drug free. I'll put that on as my day goes. I know, I couldn't find anything red. I was like, where's the, like I was saying I have like a Phillies shirt or something, I think, but.
The ladybug's red.
Oh, my ladybug is red. There you go. There you go. All right, I'm shouting out to my people at home. How you doing? I got to wave. Now here's how. Let me show the kids that are in the classroom. Here's really what I normally get. I get. See. This is what I was talking to. Except Paige. Paige always had her face on. But I got everybody else has the black screens with their names. It was really hard to tell if you understood what I was talking about. Oh, thank you. I got a comment from Paige. I love it. 16, you thought section 16 was confusing or number 16? 16, the section. I'm assuming, right? Yeah. All right, so let me clear that up because the concept is extremely easy. He just made it a lot more complicated. So here's the intermediate value theorem. He says, first of all, it has to be a continuous function. If it's not a continuous function, the intermediate value theorem can't apply. It only applies if it's continuous. So, big note to be had. In my margin notes, I said the function must be continuous. And then he drew you this picture, and he said, yeah, you've got a section of the graph that you're looking at between A and B, x values of A and B, which gives you y values of f of A and f of B. And he drew the picture like you've got on there. And he said, here's what it says, the intermediate value theorem. If f is continuous from A to B, then every value between f of A and f of B exists at some point in the interval between A and B. What math jargon is that, right? Math verbiage, gotta love it. So here's what I always use as in my example in explaining this. So Freddie wrestled, right, Grace?
Yeah.
Okay, so wrestlers, right? Wrestlers, when they go to wrestle, they have to be a certain weight in order to be able to make that happen. So they have to either gain weight or lose weight. Most times it's probably lose weight to be able to wrestle in the weight range that they want to wrestle in. So say Freddie was 200 pounds and he wants to wrestle 180. He's going to have to lose 20 pounds. That's a lot of pounds to lose. But anyway, you get the idea. So he's 200 pounds. He's going down to 180. At some point, is he going to be 195.798 pounds?
Yeah.
At some point, yeah, right? At some point, is he going to be 185.742689 pounds? He's got to hit, at some point in time, theoretically, he's got to hit every weight thing between 200 and 180. He can't just jump from 200 to 180 without going through all those values. That's what this is saying, the same thing. You can't jump from f of A to f of B without going through all those y values in between.
If it's continuous.
If it's continuous. Right, that's the deal. It's got to be a continuous function. If it's not a continuous function, all bets are off.
Yeah, who knows what happens.
Right, then it doesn't make any sense then. So that's the theory we're talking about. You can't jump from one y value to another y value without hitting all the values in between if you're a continuous function. That's it. That's the concept. Okay. So the deal, it's got to be continuous. And the other thing they try to trick you on is what section of the table you're looking at. So beware of that. Because sometimes you're looking at the whole table and sometimes you're not. So that's the trick where they try to get you. So then it says all these things. On the interval from 0 to 9, what's the minimum number of zeros? Well, think about that. Zeros are where it crosses the x-axis. So in order for it to cross the x-axis, it has to change signs from positive to negative or negative to positive. You can't cross over the x-axis without going positive, negative, or negative, positive. All right, so with that in mind, here I am. I go from 1 to negative 5. Have I crossed the x-axis? Yup, there's 1. I'm at negative 5. I go to 3. Have I crossed the x-axis? Yup, there's 2. If I'm at 3 and I go to 7, I haven't crossed the x-axis. And if I go now from 7 to negative 1, I've crossed the x-axis again. So there are 3 times because there's 3 sign changes. Got the idea for that one? So when they ask for the zeros, it's how many times does it cross the axis. What's the fewest possible times? It could be 1. And this is also just between 4 and 9. So you're only looking at this section of the table. If I go from 3 to 7, am I going to hit 1? No. If I go from 7 to negative 1, am I going to hit 1? Yes. There's your answer, 1, because the y values change from 3 to negative 1 and have to go through 1. Actually, it should be from 7 to negative 1. Then I'm looking at the interval from 0 to 4. And the question says, must there be a value where y is 2? Remember, f of x is the same thing as y. So is there a y value of 2 somewhere between 0 and 4? I start at 1, I go to negative 5. Have I hit 2? Nope. If I go from negative 5 to 3, have I hit 2? Yes. Yes. On the interval, f of 2 has to be there because of the intermediate, they abbreviate the IVT, intermediate value theorem. If it has to hit every y value, then it's going to have to go through 2 if I go from negative 5 to 3. And then number 4, from 4 to 8. Now I'm just looking at these two, from 3 to 7. This guy goes. Could there be, this is kind of an interesting question, could there be a value of negative 2? Well, I'm looking at this from 4 to 8. It goes from 3 to 7. So here's my first question. Must there be a value where it hits negative 2? No, right? Because it goes from 3 to 7. It could just directly go there. Could there be? How do you know that that graph didn't do a dip-de-doo? Where's my word wall? That would have been a good one for the word wall, right? How do you know it doesn't dip down, right? You don't know that. You know it's going from 3 to 7, but you don't know if it does a little dip-de-doo in the middle. So could there be? Sure there could be. Must there be? No. Okay, there's a difference between those two questions. So yeah, there may. It's possible.
So when I say could, it's basically always yes.
Pretty much. Yep. Joey's question is when they say could, the answer is always yes, and yeah, pretty much it is. Really, that's the concept. And if you have those, then the rest of these problems are all identical. So let's do numbers. Well, you pick me. Like, pick me a chunk, like 1 through 5, 6 through 10, or 11 through 15. They're all the same question.
6 through 10.
Which one?
6 through 10.
Okay, that's what I was going to pick too. 6 through 10, just the middle guy. The questions don't change, kids. They're pretty much the same thing no matter what.
Pardon the interruption.
Ah.
Just a reminder to please wipe down your desk and area before leaving class today. Once again, a reminder to please wipe down your desk and area before leaving class. Thank you.
I think we can do this real quick. Number 6. I am continuous. I am negative 7 to 1. That's these first 3 guys. What's the fewest possible times it could equal 3? I go from 2 to negative 5. I go from negative 5 to 6. 1. They didn't ask me for an explanation, but it's because the y's changed from -5 to 6 and have to cross through 3. Like, you know, we're not going to have time probably for all of the explanations in the midst of this, but 1 to 11, that's now these last 3 boxes, only these last 3 boxes. Must there be a value where it equals -2? 6 to -1? -1 to 10? None. If it was a could, you'd say yes. -4 to 2. -4 to 2 is the middle of the chart here. What's the fewest times it can equal 2? I go -5 to 6, I can hit 2. I go 6 to -1, I can hit 2. So there's 2 times. On the interval from 1 to 11, could there be a value where it equals -2? Sure, why not? It could do another dip-de-doo. And number 10, on the interval, what's the minimum number of zeros? How many times do the signs change? So I'm going from -7, it's a whole chart. So sign change 2 to -5, there's 1. -5 to 6, there's 1. 6 to -1, there's 1. And -1 to 10, there's 1. There's 4 times. Holy moly, 4 times. All right, these 2 assignments are due by tomorrow midnight. Does that make 116 better, my friend Paige?
Yeah.
Yeah, I think his explanation was like making it way harder than it had to be.
Yeah.
You'll see on my answer key, I did do explanations for all of these, and it's probably a good thing to get in the habit of doing, but for sake of time, we did not do that. So I will see you again on Wednesday at 9 a.m.
Are the courtyards open?
Yes, courtyards are open.
Joey Garrett! Joey!
He's hearing you.
You guys need to come to school.
Yeah, you guys got presents today.
Actually, I think Griffin's B-Day. Never mind.
Is he a B-Day kid?
Are there more people this class than that class? The B-Day?
Yes. Yeah, my B-Day is 3 kids. B-Day's 3. Isn't that crazy? You are 1, 2, 3, 4, 5, 6, 7, 8, 9. You're technically 9, and they're 3.
That's pretty.
Who's
Sad for
missing
them.
from our group? What? No, that's the F1. It's one of the, it's either the ones on the end.
Wait, Grace, where are you going next?
But
The middle one's up.
I guess I can walk.
just Paige. Paige has gone virtual
Oh, okay.
for the moment. And John is virtual too. It was fun mathing with you today.
Do you have a lot of all virtual students?
I'm pretty mixed.
I feel like in a lot of my classes, there's more than all virtual.
Oh, really?
Just like
Yeah,
one
I have
virtual.
If you look at the red on the side, they're my virtual kids in that class. So, like, you guys only have John. John's your only virtual guy. But I think he'll be coming back probably after the marking period.
Cross.
All right, kids, have a good one. I will see you. I'll see you virtually on Wednesday. Bye. You too.